Underneath the layers of paint, Van Gogh's sky vibrates with the principles of real-world physics. Greetings to everyone. Today's video focuses on how Van Gogh's brushstrokes in The Starry Night create a remarkably convincing illusion of movement in the sky, prompting researchers to explore its alignment with the physics of actual skies. Specialists in marine sciences and fluid dynamics have analyzed the painting to reveal what they refer to as the hidden turbulence within the artwork. By examining the brushstrokes, they assessed the shape, energy, and scaling of atmospheric properties in the otherwise unseen atmosphere, utilizing the relative brightness of different paint colors as a proxy for the kinetic energy associated with physical movement. Now, without further delay, let's dive into our discussion. The brushstrokes of Van Gogh evoke such a realistic sense of movement in the sky that they have prompted atmospheric scientists to question how well they correspond with the physics of actual skies. Although the atmospheric dynamics depicted in the artwork cannot be quantified, the brushstrokes themselves can be analyzed. This week, an article in Physics of Fluids, published by AIP Publishing, featured researchers from China and France who specialize in marine sciences and fluid dynamics. They examined Van Gogh's artwork to reveal what they describe as the concealed turbulence in the artist's portrayal of the sky. The size of the paint strokes was essential, stated author Yongxiang Huang. Using a high-resolution digital image, we could accurately measure the standard dimensions of the brushstrokes and contrast these with the scales predicted by turbulence theories. In order to uncover concealed turbulence, the authors employed brushstrokes in the artwork that resembled leaves caught in a swirling wind funnel, allowing them to explore the shape, energy, and scale of atmospheric traits within the typically unseen atmosphere. The differing paint colors' relative brightness, or luminance, served as a substitute for the kinetic energy associated with physical movement. Huang stated, "There is a profound and instinctive grasp of natural events revealed in his work. Van Gogh's accurate depiction of turbulence could stem from observing the movement of clouds and atmospheric conditions, or from an inherent ability to convey the sky's dynamism." The research focused on the spatial dimensions of the painting's 14 primary swirling forms to determine whether they correspond with the cascading energy theory, which explains the transfer of kinetic energy from larger to smaller turbulent flows in the atmosphere. The researchers found that the broader image corresponds with Kolmogorov's law, which forecasts atmospheric dynamics and scale based on observed inertial energy. By examining the microcosm present in the paint strokes, where the canvas exhibits a diffusion of relative brightness, they identified a correlation with Batchelor's scaling, which outlines energy principles in small-scale passive scalar turbulence that follows atmospheric movement. Discovering both types of scalings within a single atmospheric system is uncommon, and it served as a significant motivation for their study. Huang stated, "Turbulence is thought to be an inherent characteristic of high Reynolds flows where inertia prevails. Yet recent findings have observed turbulence-like behaviors in various flow systems across a broad spectrum of spatial scales, even at low Reynolds numbers where viscosity plays a more significant role. It appears that we need to put forward a revised definition of turbulence that can encompass a broader range of scenarios. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance."